Welcome all. In the interest of time, yeah. So let's welcome our speaker, Professor Shantanu Sarkar. So he will be talking on machine learned systems in industrial automation.
Hello, hi. So my talk would be basically a more of a high-level, broad perspective of machine learned systems in industrial automation based on my personal experience, and of course, I have been involved in shaping up various research areas. So that gave me an insight, and I'll be sharing that. This will not be really something deep in terms of taking up one particular problem statement and then doing something. I will plan to do that sometime later in some of the talk. So okay. So this is again is what we could see. This is not kind of taken from any of these standard Gartner type things, but it's more of internal thing where we kind of created this. So what we did is we basically looked at specifically with respect to industrial systems that there are various AI machine learning topics that are finding their interest or emergence, and what are those topics that are relevant today, as in at least 2023, 2024, and where all one should focus on was the kind of exercise. And what we found is that out of various topics, the ones that seem to be quite important with respect to industrial adoption, by talking to, of course, the partners who are actually deploying solutions on the field. So we believe that areas in the context of edge AI, data-driven AI, end-to-end ML lifecycle management, automated learning, and explainable AI are at least seem to be quite hot, and at least the product groups who are building product solutions, they are interested to at least take these things forward, as opposed to federated learning or reinforcement learning. So that doesn't mean that they are really not less impactful, but at least with respect to industrial systems, they're still maturity level is not that high. But still, I will talk about a few of them in this talk. I mean, in terms of what are the ideas or what are the kind of research topics that one can look into. So basically, there are four pillars that basically drive this thought. One is the scalability. Basically, more than a machine learning algorithm, people are more interested in building an end-to-end solution which can scale up, which can be deployed on a cloud-based systems or edge cloud-based systems, and also at least in a context of industrial automation, people are building now smart devices where they would like to deploy at least tiny models on resource constrained devices. So that is basically the solution need to not just scale up but also run on those. And of course, we all know that having data or having good data is a problem. So can it be used with small data? And secondly, if we build a solution for one class of industrial assets, can that be extended? Then, if it has to run on an industrial system and specifically with focus towards Industry 4.0, which is actually focusing on automation. So, of course, reliability is a very important pillar where once you deploy the model, then more or less it has to take care of itself in terms of whether the model performance is doing okay, or if it degrades, how to improve that automatically. So that's an important area that are in the focus. Then data quality, more than the model, it's more of a data quality. ensuring that all the time is also important. Detecting drift in the data, and then warning that early to the MLOps engineers. Then one of the biggest challenge in deploying ML solutions in industrial systems, and possibly it is true in other domains as well, that it acts kind of a black box. Therefore, interpretability is important. And specifically during training and operation, if a bit more explainability is incorporated, that would be quite valuable. And in fact, my personal experience has been that a lot of the folks who are actually deploying solutions, they are very hesitant to deploy such solutions because of the black box nature. And of course, human understandable explanation. That's another focus area which personally, I never realized that this is an important topic, but specifically when you are actually monitoring certain plant execution or execution of a system, and then your ML-based system basically flags an anomaly or warns something, then many a times operators do not really trust that. So therefore, providing an explanation as to why this has happened, and specifically linking that with the past behavior or past failures sometimes help, and that's what has also been an important focus area. So again, the predictions that are there, is it reasonable, and can some confidence be instilled there? Yeah, usability in terms of again incorporating domain knowledge and incorporate that in the model, and of course automate the model training based on data characteristics, which is kind of auto ML, are important focus areas. In fact, I think Ashwin, you had been looking into this domain knowledge based learning, right? So I think that's quite cool. Which one? The domain knowledge? Which one? The domain knowledge based thing? Yes. Yes, that was no. But the thing is, at least what I see in 2023 and onwards, some people are actually now talking about doing this, and they would like to investigate this. So while while this is so those heat maps are essentially created by looking at past 2 years of usage and talking to people. However, they find that this seems to be an important topic that they need to take it forward. So yes. Yeah, so when we're talking about reliability, it's of the model and model-based systems. But as you said rightly, yes, industrial systems are definitely reliable, and they use traditional reliability techniques, specifically using kind of redundancies and many other stuff. But what happens is that what I understand. Okay, so one example I can tell that let's say these controllers. So controllers are basically hardware or hardware-software combination where hardware plays a very important role. And because of this green initiatives and because of many other things where either, one is green, another is kind of profitability. They think that having this controllers which is hardware-driven, mostly hardware-driven, is not sustainable. So they basically go for software-driven controllers. So the moment it is software-driven controllers, then of course you have to take care of the reliability there. That doesn't mean that you have to employ AI, but traditional software reliability will definitely come into play. But what I'm talking about here is that in addition to this controllers which are actually controlling, let's say, a lot of devices and data is coming, you are going to let's say replace human, or at least a lot of human, with ML-based monitoring systems, tracking systems, right? So, and they need to run all the time. And it's not that just they don't fail, but also they do not give incorrect results over time, or take incorrect actions. So that's what I mean. And of course, suppose that I'll talk about this a bit maybe later. So if I have time, specifically in the AI at the edge and distributed learning, if I have time, I'll speak about it. So basically, use of AI techniques on actually IoT endpoints and devices where the data computations are happening. That's what is the AI at edge, and that's definitely an important area. I did work on this topic a bit. The main driving factor is the low latency analytics, meaning that you need to take the decision real fast. There are some scenarios that there has to be done. So collecting data, and then taking the inference there itself is an important requirement. And then there are tiny ML advances. So tiny ML essentially are really tiny ML footprints on small devices, and making it smarter. So those are basically driving factors. And so by plan, I mean, what are the ideas that one can perceive here is that, for example, predictive health monitoring is definitely an important area to be looked at, and the machine learning solutions for that. That's definitely an important research area. Then distributed learning techniques, again, on edge sensor combined, edge sensor cloud combined is also a hot area. In fact, a lot of work is going on in various other companies, specifically Samsung, for example. They are working on that. With respect to companies like Siemens or ABB, they do not have a requirement of resource constraint devices, mainly because with respect to battery power, because their use cases are all actual plant. I mean, it's not really kind of moving, so the power supply is always there, but the devices may be tiny. So that's one. But for Samsung and other companies, are specifically Siemens, they have both the scenarios. Then yes, resiliency during learning and prediction. So those edge devices can actually fail. Specifically, we are talking about when we are talking about deployment at large. So while doing the learning or I mean training, or even doing inferencing, if it fails, how do you handle that? So these are basically the research areas that one could look at. Now, another interesting topic that, again, I mean, I was not that aware of until I interacted with a few people, that basically a shift is there in terms of focusing on optimization of an ML model, and the focus is going on more towards data that is used to train the model, and making sure that that data itself is good. And that's a huge demand, actually. So people are almost saying that I'm okay with any out-of-the-box ML solutions, but can you ensure that the data that I'm getting is actually curated, cleaned, and it doesn't have noise, and also an important topic of few-shot learning. So essentially, few-shot learning is also a topic that seems to be of interest to quite a few people, where you take a very small set of data and then basically try to learn there, and then have a baseline model, which is not too bad, but and then deploy it, and then as and when you get more and more data set, you can improve that. So that's then second is that in absence of real data, take a small amount of data set, and then we have a more robust mechanism to actually generate artificial training data generation. I mean, of course, GAN is one way to do it, but any other technique, and in fact, people are focusing on those areas quite actively. Then data drift analysis, which can actually cause the model to misbehave in real time. Detecting that is also an important area that people are looking at. So these are either being explored as research projects or kind of given to universities as PhD topics or master's thesis topics, as I can see. So in the context of edge AI, I actually looked at a federated learning based approach. So to a small extent, again, I must say. As you know, that this is kind of attractive proposition, specifically because the data lies with the customer, and then even for this specifically, we have seen the customers like energy or utility, specifically energy, oil and gas, electricity generation, power plants. Those guys are extremely finicky about their data to an extent that they basically have their own very secure plant area where you have sensors, and they just do not want the data to go out. So therefore, building model in the cloud is out of question. Not just that. So that's one use case. Second is that at least in the case of industrial plants. So there are, say, if a huge plant is there, which is having, let's say, around maybe 50,000, 70,000 even devices which are being monitored by I don't know, maybe 10,000, 20,000 controllers, and there are different parts of the plant. Okay, so they are kind of similar in nature. So they're similar, but they are physically different. So in that scenario, you can basically use this kind of decentralized learning, where you could have, I mean, each of these similar places, you can have localized learning and then kind of aggregate that. So those are interesting use cases where federated learning can be explored. But again, it is not in the heat map, simply because when I tried to push this when I was there, and then they are very resistant towards this. I mean, they according to they meaning the people who are actually on the field, they, according to them, deploying the more basic model, ensuring that there is no drift, are more important than doing this, because they see this is coming only in next 5 years, not right now. But again, I mean, as a research topic, that's certainly an interesting area. So I did investigate areas in the case of hierarchical edge, and then deploying federated learning in the context of hierarchical edge devices, and also changing the topology of this like distributed edge devices. Yes. No. It could be extranet, but not cloud. Yeah. And then it's not that it's going on the internet. They are all yes. Yes, but okay. So the scenario is this: that there is what is called a core process control network. Okay, which is like, I mean, almost like it's a kind of closed door where nobody can enter. It's like their core area. So extremely secure, very deterministic. So data comes from there. They are so obsessed with this data part that they basically put a physical, it's called data diode. I mean, it's a physical device which basically allows the data to flow in one direction, not the other way. So they put the data diode in that closed area, so that data goes from that to the next level. So companies like, for example, Siemens or ABB or any other third-party vendors, they sit in that area, not here. Okay. So and these guys sometimes they have limited access to the data, in a sense that they can just consume it, but they cannot push anything back. So under that circumstances, when they are not able to push it back, how do you deploy? Obviously, you have to deploy the machine learning models there, not inside this. So that's also a challenge where how do you actually build model there where you are not really kind of pushing, you cannot push anything there. So I don't have answer because that's a problem we faced, and we tried to address that with the clients, and they are not ready yet. One solution is that on demand they open the other gate. Now, how do you handle that? I mean, if you are doing this continuous monitoring using ML model, and if there is an on-demand opening of the gate, uh, so can you really do this kind of cyclic learning? Like you have some edge networks here, and then you have another there, and then the data goes only one way. So you can only send, let's say, model parameters, but you cannot push it back. Or if you want to push it back, you have to push it only once in a while. Or if you are doing a centralized learning, then the model sits outside that secure area. And how do you suppose you find that your model needs to be updated? How do you push it? I mean, at least they appear to be an operational problem, not a technical problem. But I personally feel that this definitely has research component in it.
So something like you have a generic model which works for everyone, but on the local machine, that model should learn how you.
So that could be one way, where you have a generic model and then copy that to those local places and never communicate and let those local guy model fine tune itself. That is completely isolated approach. But supposing that they want to interact with each other. Teach each other.
Okay. So then like this. So what are they allowed to share? I mean, are they allowed to at least send the links of the network?
I mean, that's something that it's a kind of a gray area today. Maybe we can discuss that later. Because I wanted to cover a few more areas. Okay, but I'll kind of come back to you on, because I have to give a long answer. I can't give you one line answer there. Yes, but I have experience there. I'll tell you that. So domain knowledge in AI models, again, this is something that I know for sure that a lot of engineering companies are working on it. Not just Siemens or ABB, but even like Volvo and Daimler Chrysler, or even automotive companies. So here the idea is that you have less data, but more domain knowledge. So for example, you have this computational fluid dynamics solutions using Navier-Stokes equations, right? And you solve it using numerical methods. Now, question is that, yeah, of course, and that's most accurate. I mean, right? But if you want to say that I want to implement using machine learning, okay, and you want to use the properties of those CFD things as a part of your ML model, then what do you do? And why is that important? Why can't I just do it using ML? Because ML is completely data driven, whereas it really doesn't know the physics of it. Okay, and the idea here is that you and in fact this is a very recent research topic, which is the physics informed neural network, where for example it is very much useful when you want to build up a very faithful what you call it surrogate model, or digital twins, right? So if you want to build a digital twin, today I know that digital twins, they are talking in the future that in industry 4.0 there will be digital twins for almost every like hardware asset, like, but in reality other than, let's say, very simple motors or maybe some safety tank or whatever, they really have not been able to build a faithful digital twin, or rather faithful surrogate model, which is completely physics based. And the group with whom I interacted in the past, they just do not want to work with ML people. They want to build a physics based model. Now today, at least this sort of approach where you actually incorporate the physics part with the ML model, so that you require less data. And then one of the ways, of course, is to basically use your um, uh, during a feedback part, right? You actually use this physics knowledge there to make it better. That's one of the ways to handle this. And I know that there are a few research explorations happening in this area. And this is a interesting topic, specifically in the context of if you want to build a model which is more complex than, let's say, things like motors, where you have where the faithful physical models exist. And what they're talking about is not just very approximate behavior. They want to get a very accurate, kind of behavior there. So they are trying to mix this.
Professor Snehanshu has a
Question. Yes. Okay.
Yeah, Professor Sarkar, in this particular context, because what is happening now, since you mentioned the Navier-Stokes, right? Now there are several such partial differential equation based models with different sorts of initial conditions.
Yeah.
My understanding is that even if you the generalist idea that people are pursuing this is that they are hoping that a general physics informed neural network model would actually handle different types of CFD flows with different types of initial value and mixed boundary value problems, right? But to your understanding, do you think that's even a feasible idea, or is it like a wild goose chase? Because it seems to me it's a wild goose chase simply because of the fact that many of these different models, including some of the ocean wave models, which are also computational fluid dynamics models, right? They
Yeah.
don't even admit of analytical solutions, and they are not continuous in nature. So I'm sort of skeptical about this. So I just wanted to know what is the industry's opinion about this.
My experience is quite limited, Professor Saha. So what I know is that there are groups, again, I mean, in the Astral company, there are groups one group who is actually expert in this control and optimization, who basically looked at physics-based solutions. And they have actually deployed, or they have helped people to build smart motors with its, digital equivalent using physics based, like physics using physics plus control theoretic approach. So they are now saying that they would like to work with this ML group, and then would like to give their expertise to build a joint model. And it has started. I don't know if they have been successful, but they think that they can do something, and they are going ahead with this kind of project. So it's a completely exploratory project. I don't have answer. I don't know.
Okay.
AI rates. And I didn't see that happen. It might be just big demo, but it was a demo. Something for doing some happen.
Yes, they did build it. Those are at least what I saw. I also haven't seen it very deeply. I saw in one of the conferences. So that's again more for training purposes, and more for usability thing. That suppose there is an operator who wants to understand the behaviors and so on, so they can do this kind of question answer. It gives it. But supposing that you want to really do a serious stuff, let's say. You want to put at least it's say one scenario is that suppose you have a complicated machine for which there is a digital twin, and you want to put both the digital twin and the actual thing into the plant, and let's say the digital twin is integrated in somewhere else, and that is actually taking decisions based on whatever is happening there. So this guy has to mimic its physics. So there, it's not there today. Only in motors, I know that it's there. That too for just collecting data.
If I don't do that, so the practical small oil test that I've done with the boiler type system. Comparing a physics infrared driveways with the network. Really where found that the neural network was quite closely matching the physical. Quite complicated differentially. It's my she was talking about somebody wanting to do work on it.
So then this particular project that I'm talking about, or rather this particular theme I'm talking about here, okay, sorry, before that, Sahar, do you have any other question? I kind of
No. Maybe you go ahead, and we'll discuss later.
okay. So so this one is I mean, this theme is called Safe AI, where again it needs to be reliable and safe, and okay, so I mean, I'm not reading the slide, but I would like to highlight one point is that so in the case of so when I have written the plan, I have two thoughts in mind. One is purely from software engineering, software development point of view, and another is possibly AI ML point of view, or maybe another one is a combination of two. So even today, for example, in the mainstream AI adoption scenario, so exactly what are the risks that are there when one wants to adopt the AI, and those risk categories, what are those? Is still not very clear. I mean, there are some blogs here and there, but we really do not have that laundry list of really concrete, well-defined set of risks that are there that need to be addressed. So if we have that risk, then possibly we could address, or those addressing each of those risk points could be an interesting research topic. But we still do not have that so-called requirement here. And of course, you know, what are the gaps today? That's not there. However, there are you know, very I mean, you know, like ABB, for example, or Siemens, they all have their cloud-based solutions, which actually they give it to their clients, and those clients are primarily really engineering companies. So, and through that portal, they basically offer ML-based solutions. And for example, things like uncertainty quantification is one of the areas that they are looking into today. Where they would like to basically, at least when they're simulating, for example, or they want to build a simulation model, in that context, quantifying the uncertainty in a more metric-driven way is what people are trying. Then subpopulation analysis is the one where it tries to see that whether the solution has any bias towards any particular population, and then so what I'm trying to say is that these sort of things, building that and then deploying it in the real time so that it can give you the answer on a real-time basis is the challenge. At least I could see that people have struggled and still do not have a proper solution. I'm not talking about doing this sub-operation analysis on a Jupyter notebook or on your laptop, but actually deploying it in the field where you have a dynamic system, and then doing that in there.
Actually deploy, they must be willing to take the risk of actually believing the uncertainty wanting the treatment. You have to need that, and they have to deploy it. So,
yes, that is definitely there, but at least
quite risk averse.
See, at least our interaction, because we are from corporate research group, our interaction was never with the actual field guys. So we were interacting with the product team, who are supposed to, let's say, finally deploy to them. So they would be facing the hit if at all. But those product guys have been saying that this uncertainty quantification is something that they believe they will be able to sell to the actual customers while deploying it.
Because Aditya and Snapshot, I think, are doing something about this. Can be deployed. And is that correct?
Yeah, go with it.
But
It is,
so it can be. They are doing a kind of. They can give a clear statement that don't use this model. And outside it's operating range as such from the this. But which seems to me a really useful thing to know. But then is that actually going to make it deploy that? So convincing industry that research is actually trying out seems to be another
yeah, recently an underground pipe movements something to do with the lift.
So there is an underground pipeline in Pune that burst and caused fatalities, and then burst strength of pipes were estimated in the DNN model. Obviously, they are far from precise. So one of the reasons, however, to model burst strength of pipes is the lack of closed form solution of the existing model. Possibly, yeah.
Anyway, okay, sorry. My point was that it's not, I don't think it's the case that there aren't real-time deployable solutions that are, they do exist, I think, but somebody has to make the code to try it out.
So, okay, when you are saying deployment, what you mean is that it's a kind of whether the client is going to allow such a solution to run.
Yeah, or even the product.
What I'm talking about is beyond that. Say, assuming that they allow you, then I mean, making it 24/7 available and then doing its job all the time in real time, and then telling you when things are going wrong or is another story, isn't it? So building that robustness into the solution, even if they say that yes,
that's a sort of software engineering issue, or that's a machine learning issue. What would that?
certainly software design issue, but I think it is beyond that. Not just is I haven't explored, but my gut feel says that it's not just a good engineering problem. I mean, a software engineering problem. It's beyond that, I guess. It has to be mixed of both.
Should be
possible the next year in Japan. There is some decades and another the system design for a design plan and one that is a design was thought through and
so that disengagement is, of course, a software part, but it is not just a good design. It's possibly
more than so the whole thing should, the whole system should be able to handle the thing gracefully. That's what I meant. It's not just the software.
yeah. But what you said that that initial resistance is also I haven't seen. I haven't seen what is the status. Have they been able to deploy it successfully? I don't know.
Because in the end, the machine learning part of it or whatever is quite small. You know, that's the ML program will probably keep doing whatever it's doing. The guarantee, it'll provide some guarantees about it. But it's all these other things.
Yes.
What happens when the machine learning model says, I'm not ready to say anything, then does the whole system collapse around it and the whole sort of network shuts down? So that's a sort of thing where the kind of design problem of how we design around state of doing or not.
Yes, so that's why at least I know that people are, or at least in ABB I know that, or when they also clone Siemens, so all this, they are not that keen in having a group called machine learning folks who are basically developing kind of a model or algorithm. They're more interested in building ML driven systems, which basically means that maybe 10% or 20% is that ML model which is actually doing its job and then saying yes, I can do, I can't do. And maybe you have some uncertain principle based solution which is giving you the answer. But then what, I mean, this kind of integrating that with the whole solution is a big challenge, and people still do not know how to build it. So that's where a big focus is today.
Dr. Snehanshu has a comment.
Yeah. That is definitely a good question there. I think his question would be more relevant to physics-driven models or but why are you not speaking?
I think there is some problem.
No, I didn't want to interrupt your flow, so I was typing. Sorry.
Managed
Yeah,
to
man.
swiftly
Yeah.
interrupt your typing. So you might as well speak now, I think.
All right. Anyway, somebody already read my question, so it's okay. No, I wish I knew the answer to my question, but I just anyway.
That would be cheating.
Yeah. I mean, I don't know. I mean, the point is, I'm not comfortable with this. I mean, the last slide, not this one. Anyway, go ahead.
Which one?
I mean, the last slide where you were discussing the, PINNs, not the safe AI. Before that, the PINNs. Yeah, the PINNs for the physics informed neural nets. It's like a, one-stop solution to all CFD problems. I don't think. I mean, it's a very, very difficult question.
I think. So
Yeah.
maybe let me try to answer this at least. See, if you purely go by physics-driven model, then I think your choice, finally the number of physical systems that you can actually model accurately would be limited. You may not be able to really do justice to many other varieties where you possibly cannot build a physics-driven solution. So, for example, let's say that you have a very nice physics-driven model for, let's say, a motor, or maybe a tank. But suppose you want to build a plant and then which has got these components, and you want to integrate them, and you don't have a physics for the whole thing, right? And then suppose you want to build a digital twin of the entire plant having these small components. Then I mean, what do you do? I mean, I don't know. I mean, I'm thinking that.
I mean, Professor Sarkar, I don't have a gripe with the physics-driven models. I mean, I have general problem with a deep neural network-based training learning regime to sort of, model these kind of solutions. That's it's nothing to do with physics per se. It's,
But I'm saying that maybe this combination, I don't know, I may be wrong, but I feel that this combination may be maybe more powerful in terms of modeling with complex dynamics.
okay.
Don't know, honest. I mean, again, I know very little about this, so I haven't really explored this. So here, of course, we know all this, ChatGPT, etc. But have you seen these, for example, custom GPT, or maybe there is an AI for that, which are all like offshoots of this ChatGPT. So this, for example, there is an AI for that. Apparently, it creates AI-based solutions almost every day, and they have built some 500-600 solutions, including all kinds of stuff. Like, for example, if you want to build your own house, you can just click the photo of your drawing room and then upload it, and it can tell you how best you can, what sort of things you should change to look it good, and so on. But again, with respect to this, with respect to the industrial systems, so one approach is that I mean, at least it is a very specific to again industrial systems. I don't know whether this can be generalized to any other places. That these companies, they have their own controllers, okay, and those controllers are basically, they have their own control languages, which are kind of pretty primitive and pretty old. And now they are trying to move away from those control narrative-based languages to more modern languages, like, for example, Python, simply because there are no people today who knows those languages. Now, they're exploring whether such kind of ChatGPT-based solutions, may not be ChatGPT, but at least things like, let's say, custom GPT, where you take the baseline of ChatGPT and kind of a transfer learning approach, where you take that and then at least the custom GPT would allow you to add your own domain knowledge there, and using that you could basically build, for example, things like a boilerplate code generation from control narratives. I mean, where you really don't have to learn the language, but from the intent you can generate it, or say service tuning of a particular device. Then using the question answer session, it can help you. I mean, operator assistance. So those are the areas where at least people are looking at this ChatGPT, and this Rubber Duck is maybe, if you have not seen this, it is a plugin today that has come for Visual Studio Code, where you can pretty much generate the code. If you just type your intent, it can give you the code right and to Visual Studio code system. So, but to my what I feel is that these requirements are more towards kind of, oh yes, so one of the good business case that I was told, I was asked to handle that honestly a few years ago. So the idea was that I mean, at least the companies like ABB, they lose a lot of money, for example, to the big client, because when they kind of provide this controller based solution, which is basically their own controller plus the software, that comes from some requirement. Okay, and that requirement is not really a very I mean, not an English thing. Okay, so it's a kind of very structured stuff, and so that from that requirement one can kind of generate the code. I mean, kind of a engineer who is trained in industrial engineering, or this stream disciplines. But the point is that there is a middleman who sits there, who basically talks to the client and translate their requirement to this thing, and everyone wanted to get into that client rather than depending on the middleman. So this to reach there, I mean, this kind of things might be of help actually. I think I have quite a few, but I don't know. I think I've exceeded my time to a great extent.
Yeah, maybe we can have another talk. So there are plenty of empty slots that we have.
Okay,
Next
so I
week
can
would be-
I can talk about those later, and maybe some of at least the edge AI work that I have done. I can talk about that.
So, if you wanted to track industrial projects, what would you suggest work on? From our side,
Yeah. So, I mean, maybe very quick answer to that is at least whatever I heard is like this domain knowledge driven machine learned systems is one that they would like to explore this with academia. Physics informed models and I think these two are for sure. I know that they would be interested to kind of explore. Then shifting model to data is also a theme that I hear, not just here, but I mean, I know that in IBM labs, they're also working in these areas. I don't know whether TCS research is also giving importance to this. So those areas could also be of interest.
So what it's all about collecting data now.
No, not just collecting data, but essentially ensuring that the data that you collect, one is looking at the quality of the data, looking at after training, for example, if you know that, okay, so supposing that you have a data and then how much data do you really need to train this? If you don't have enough data, what are the alternate mechanisms like to actually train the model? Then suppose you already have a model and then the real-time data is coming out using which you're doing inferencing. You detect the drift in the data in real time and then kind of alert. So those kind of stuff.
But these are people who do that.
No, machines doing that. Yes, they are. Yes.
On the industrial sector.
I think I don't remember who all exposed this. I think ABB they themselves give some open data, and a few other companies also. I think Google also has it.
Matrix. That's the standard data.
But the ABB dataset is on industrial systems like temperature sensor or motors or things like that.
No, it's on image.
No, I'm saying that what? Yeah. And there are some open source tools which are drift generators, which you can use on any data set and use that. And they're all like kind of not certified, but they're well acknowledged by people. So you can use that and then put it on a real data set, create a drift. You can say that I want 10% drift or whatever. Some give some hyperparameter and then it will give you a new data set with a drift, using which you can test. So, I mean, if you're saying that you want to test your approach and then want to kind of publish, etc., you can refer to those tools saying that I use that to inject a drift.
Any name they should Google?
I should be able to tell you, but I don't remember it right now. I can tell you later. Off the top of my head, I don't really remember.
We were looking for something of that sort, and we were trying to generate them with the
Even
drift,
drift generator.
Yeah. I mean, so whenever you remember, you can probably
Yeah,
we can
sure.
connect again.
GAN to generate trips.
You know, I mean, see, the whole point of identifying drift is to identify neural network. Right? You can use a neural network to generate a neural network. That would be way too complex.
I think one tool does that.
Sorry?
One of those
one-
tools does that.
What is it?
Oh, it uses a neural network to generate.
That's what I'm trying to say.
That would,
I don't know.
I mean, how?
Yeah, I got your.
So the drift here is about what the data distribution.
Yes.
Distribution.
I think you can GAN to do that. For instance, to evaluate a model.
I got the question of real.
So somehow it should simulate a real.
But the way we add noise. I can add data. How do you add the data?
Yeah, we can sort of, if you use GANs for it, it other purpose because you know what you're waiting for.
No, GANs is not used for drift. It's used for kind of generating that data. I mean your point was that the data drift generator tool, right?
Yes.
Yeah. So I'm saying that I mean I have heard that. I mean I'll tell you some of the open source. I mean, of course, I would not be able to give you any closed source tools, but open source tools are there. And I know that one of the approaches did use some neural net based approach. I have not really looked at it.
One thing that we talked about, which I presume doesn't figure that is it did figure, but I didn't see how about human in the loop system. Now these not of importance to industry because you did say something about requiring human understandable models. Yet figure it maybe like
I had one slide which is about explainability, human understandability.
yes, but where are they figuring? Are they operators so large so can it what?
No, they are not operators of plant. They are more of so operators are guys who are basically just to observe things and then if things happen they actually react. But there are some engineers who are there who are also in the plant, but they are not actual operators, but they look at this kind of stuff. It is
So
for them.
the physics-based model understandable. That you're talking about.
So the understandability, at least what I have seen, is limited to offering an explanation as to why, what are the reasons why it did that, Yeah. So at that level, so not just giving feature importance, but slightly beyond that. For example, one example I can tell you that there is, in fact, that is being productized. That suppose that the model says that this there is a problem in this, or this part of the plant of these sensors have some problem, or this action that is happening is really not normal. Then I mean, beyond that, what happens is that it uses some knowledge base, for example, which basically goes and searches that knowledge base and then see if such past incidents have happened which is of similar type, and then augment this particular decision with the past data, saying that in the past something similar has happened, and that's how the human in the loop, as in it's being explained to the human.
So in that sense, in what way a differential equation model that has no real closed form solution explainable. Even their heads, I mean, so when they were happy to accept those models, why are they unhappy about this one?
Maybe because those are like, they are there for a long time, they have been tested and so on, so they have some trust built into
The
it.
paper, scientists very last year, right? So, saying that no one really can explain why things stay up.
Okay.
Apparently, there is no sort of human understanding. I mean, we do have this values of very kind of models, but there are two competing human understanding models, and they are contradictory to each other, and nobody really knows what. So, I mean, it's a little it's sort of strange that people engineers are able to accept models which they actually probably can't even understand themselves. They're just going on some kind of past reputation that Andrew Stokes must be all right.
Yes.
So I think it's there's some amount of understanding.
I don't know, maybe if these models, which are data-driven models, if they are, they can establish their, reliability and all this stuff. Possibly, I don't know, maybe what.
Yeah, I mean, if there was a closed form solution, then somehow that people may not understand it. Some very long form of integration as a closed form solution is it's why. And they don't really agree. I don't know why, but works. Maybe there was not
Are there any questions from people who are attending remotely? Maybe. I think that's all we have. So let's thank the speaker for a very informative talk. So next week we won't be having a talk.